Okay, the next thing that I want to talk about is what we call as rationalizing the denominators. So let's go ahead and see what that is first. When you are rationalizing a denominator, the idea is basically removing radicals from the denominator so that your denominator contains only rational numbers. And since you're removing radicals and leaving your answers with rational numbers, that's why the process is called rationalizing the denominator. Okay, and the first few examples that we will look at have only one radical term in the denominator. So, something like this example here. So we want to know how to rationalize this denominator. It's really straightforward, especially when you have only one radical term in your denominator. So since we want to get rid of square root of 3, now we know the only way that you can get rid of square root of 3 is by squaring it, right? So if you have square root of 3 and I want to make that a whole number or an integer, if I take square root of 3 and multiply it into square root of 3, I will end up with square root of 3 square, right? Square root of 3 times square root of 3. And we know that the square is the inverse of square root, and you end up with 3 as your answer. So this is the logic that we apply when we are talking about rationalizing denominators. So let's go ahead and see how this will work with our current example here. So I take my denominator and I multiply it into square root of 3. Now remember, since this is a fraction and we don't want to change the value of the fraction, we still want the fraction to have the same value as 15 over square root of 3. If I multiply my denominator by square root of 3, I have to multiply my numerator also by the same number. And what this will do is when you solve this, is you will end up with 15 times square root of 3, and on the denominator you end up with square root of 3 square, right? Just multiply across, and then your square cancels out your square root, and you will be left with 15 over 15 times square root of 3, and the whole thing divided by 3. Okay, so basically we just got rid of the radical on the bottom. Now normally we would leave our answer in this form, but you can see that 3 and 15 can reduce each other because 15 will go into 3 5 times. So we'll go ahead and reduce this, and once you do that, you will end up with 5 times square root of 3. So you still multiply the 5 back into the square root of 3, and your answer will be 5 times square root of 3, and that's what we're looking for. Okay, let's look at another example to see how, again, this whole process works. This time we are talking about negative 5 over square root of 24. Now, if you look at square root of 24, you should be able to see that, okay, maybe this is one of those denominators that I can maybe simplify before I go ahead and start solving this problem. So how about we go ahead and, let's say, break down our negative 5 over square root of 24. I can write 24 as 4 times 6. And again, why 4 times 6? Because 4 is a perfect square. And that will give me negative 5. Square root of 4 can come outside as 2. And then you will be left with square root of 6 in your denominator, okay, with your radical sign. Now, just like we did with the first example, we'll go ahead and multiply with the radical term. Now, 2, you don't have to worry about it, okay? because 2 is not in the radical. We already brought it outside the radical. So the only difference here would be now I will multiply by square root of 6. Okay? And that will give me, again, negative 5 times square root of 6 over, don't forget that 2 in the front, and then square root of 6 squared, and then the square will cancel out the square root, and we end up with negative 5 square root of 6 over 2 times 6. 2 times 6. And if you take it another step, your numerator stays the same, negative 5 square root of 6, and 6 times 2 will give you 12. And that is the answer that we're looking for. Now you can see 5 and 12 cannot reduce each other because 5 will not go into 12. And that's why in this example, we'll go ahead and leave our answer like this. Now, if that was like a 9 and this was a 12, then of course you could go ahead and reduce it down further. But in this case, you can't, so you leave it right there. Okay, we'll go ahead and take a look at this example here, times square root of 6, which will be, now this one has a variable in it. So let's go ahead and see how you work with variables. So you have square root of 24 over square root of x. We'll first go ahead and apply the quotient rule and go ahead and break these down into 2 separate radicals. So instead of leaving it as 1, we'll go ahead and break it down into 2. All right. Now, we just saw how to simplify square root of 24. We did it right here. So we'll go ahead and do the same thing for this numerator here, and you will end up with, again, 4 times 6 over square root of x, which gives us 2 times square root of 6 over square root of x. Okay? Now that we have simplified our numerator, let's go ahead and rationalize this denominator. And how do we do that? By multiplying by your radical in the denominator. So we go ahead and multiply our whole expression by square root of x. And let's see, on the numerator, again, since they have the same index, you can multiply the 6 and the x, and that will give you 2 times square root of 6x. Okay, basically you just multiply these two, and the denominator will of course give us square root of x, the whole thing squared. Again, 2 and the square root will cancel out, square and the square root, and you will be left with 2 times square root of 6x and the whole thing over x. Now I know many of you will be tempted to cancel out this x and this x, but you can't do that because this x on the numerator is inside the radical sign. This x on the denominator is by itself, okay? These are not the same things. You're basically saying square root of x over x, okay? Not the same thing. You cannot cancel these two x's out, so be careful. Don't get too tempted. All right, we'll go ahead and take a look at one more example, and then we'll move on to something different. So let's go ahead and take a look at this last one here. This time you have, again, you can see you have a variable in the numerator, variable in the denominator. Again, start by applying your quotient rule and split this up into 2 radicals. So you'll have square root of 242 t to the 9th over square root of u to the 11th. Okay, now let's go ahead and see if we can simplify our numerator any further. So how about we break down that 242. Now again, this will take you maybe a couple seconds here to figure this out, but 242, you can break this down into 121 times 2. Why 121 times 2? Because 121 is the perfect square of 11. 11 times 11 will give us 121. So 121 times 2. Now you will notice with your variables, you have t to the 9th and u to the 11th. They are both odd numbers, and we know square root is an even number because it's 2. So to simplify our variables, you want to try and break these exponents down into even numbers and odd numbers, a combination of even and odd, because even numbers will go easily into square root of 2. So for t to the 9th, I'll go ahead and break this down into t to the 8th times t to the first power. 8 plus 1 will give us 9. You don't have to write that 1 physically. It's understood that you have a 1 here. Now, why do we do that? Because 8 can go easily into 2, which is the index for your square root. Do the same thing for u to the 11th in the denominator. You can try and break this down into u to the 10th times u. Again, 10 plus 1 will give you 11. Okay? So now let's go ahead and see how we can simplify this. Square root of 121 is 11. Square root of 2 will stay inside. You cannot break that down any further. But what about these guys here? What about t to the 8th? Again, remember, t to the 8th under the square root is the same thing as t to the 8th over 2, right? Instead of writing it as a radical, go ahead and write it as a rational exponent. So t to the 8th, you can write that as 8 over 2. So that took care of the 121 and t to the 8th. We are left with 2 and t. Now, since t has an odd number power on it, you cannot bring it outside the radical. So we will leave the 2 and the t inside our square root. Okay? So out of the 4 terms, we brought 2 out and 2 got left behind. A similar thing will happen on the denominator. Now u to the 10th, since 10 will go into 2, you go ahead and write that as 10 over 2 in the exponential form. And since u is only to the 1 power, and you cannot reduce 1 with a 2, go ahead and leave it inside the radical symbol, okay, inside the square root. And let's see what you end up with. Now, all you have to do is simplify your exponents here. So you will end up with 11. 8 over 2 will give you 4. Okay, and the square root of 2t stays. And then for your denominator, 10 over 2 will give you 5. So that gives you u to the 5th square root of u. Now, we haven't rationalized the denominator yet. All we have done is simplify this problem, okay? All we did was break down this problem to a point where you could go ahead and rationalize your denominator. Now, once you do this, you will see that you are left only with the square root of u on your denominator. So, to rationalize your denominator, all you need to do is multiply the whole fraction by square root of u. Okay? And let's see what happens once you're done rationalizing it. Again, square root and square root, so you can go ahead and multiply the 2t with the u, and you will end up with 11 t to the 4th square root of 2t u, all under the same radical. On your denominator, you will end up with u to the 5th times square root of u to the 2nd power. Okay? Again, the 2nd power will cancel out the square root, and you will be left with, let's see, 11 t to the 4th square root of 2tu over, let's see, u to the 5th times u. And again, u to the 5th times u, you can go ahead and combine that, and your final answer should be 11 t to the 4th square root of 2tu, and the whole thing over u to the 6th. And that is going to be your final answer for this problem. Okay, so some of these problems may involve simplifying them till you get to a certain stage like this, and then go ahead and rationalize them once you get to that stage.